Hi there. Welcome to lecture 15 of Fox. We are going to be talking about probability. So this is the beginning of our module on probability. Now, look who has shown up for this lecture. Orange Malik. So that, that tells you something. Probability is important. Okay. Now, we're computer scientists. We are writing programs to solve problems in the real world. Okay. And we have to accept that in the real world, things are random. Packets sent across the internet, some of them get dropped. When you try to access the Wi-Fi, sometimes you succeed, sometimes you fail. And multiple people might try, and the number of people who might try at any given instant is kind of random. Okay, so this word random is thrown around a lot. Okay. And so, that's because the things that happen in the real world are, in some sense, random, whatever that means. Okay. And if we want to know how our algorithms behave in the real world, we need to deal with this randomness. We need to analyze our algorithms in the context of this randomness that exists in the real world, whatever randomness means. Okay. So probability is absolutely essential for knowing how algorithms will work in the real world. But we've come around full circle now, and today we find that certain problems are very hard to solve until you inject a little bit of randomness into the algorithm. So it's not enough that the world itself is random. Sometimes we have to inject randomness into the algorithm in order to make it behave well, even for non-random inputs. Oh, so I'm gonna let that sink in. What? Yes. So many of the algorithms that, make real-world applications go have randomness built in. So the output of the algorithm, it can be random, or the running time of the algorithm can be random. And without the randomness that's injected into those algorithms just don't go. And so, not only is probability relevant for knowing how your deterministic algorithms will behave in the real world, probability is relevant because it makes algorithms that wouldn't otherwise work very efficiently work pretty efficiently by injecting randomness into the algorithm. And then to analyze such randomized algorithms, we need the tools of probability. So probability has just become a very important tool in computer science. And, that's why we have Orange Malik. Okay. Now, what does random, or what does probable mean? Well, Aristotle said it. The probable is what usually happens. Is that okay? So we are not going to focus on the philosophy, the axiomatic development of probability. So we're going to treat probability as this important tool, and there's a sort of a mechanics, a certain arithmetic in probability. So there's a mechanics to computing probabilities. So this mechanics, this arithmetic, gives us a prescription for computing certain numbers that represent the outcomes when randomness is present. And so we're just going to use that arithmetic, we're just going to use that mechanics to compute these probabilities and see how we can use them to understand, things that are going on in the real world. We're not going to, we're going to leave the philosophizing and etc. and axiomatic development to the mathematicians. Okay? We are going to focus on the mechanics of probability. And, in the realm of, probability, you can illustrate all the ideas and all the essential tools using what's called discrete probability. And this is a course in discrete math, so it's only appropriate that we focus on discrete probability. So that means probabilities where we're dealing with discrete objects. Okay. All right. Now, before we start going on probability, a related topic is actually counting. So let's just review what we did last lecture. So last lecture we talked about counting. We talked about counting sequences with and without repetition, subsets with and without repetition. Anagram sequences with a specified number of, each type of object. Okay, and the essential idea is when you count, complex objects, you can think of constructing a sequence of instructions to construct the object and then count the number of ways of implementing those instructions. Okay. Then we introduced a sort of an advanced technique called the principle of inclusion-exclusion. Essentially, it's a way to extend the sum rule. So the sum rule is the fundamental rule. You can even derive the product rule from the sum rule. So the sum rule is the fundamental rule, but the sum rule applied to disjoint sets. So we discussed how to, extend the sum rule to the case where the sets are not disjoint, and that became the principle of inclusion and exclusion. So that's a pretty powerful technique, but it's a little bit more of an advanced technique. So you'll need a little more practice with inclusion and exclusion if you want to get good at it. So do the exercises in the previous chapter. also talked about the pigeonhole principle. That's not an advanced technique. That is a very simple principle, but it's a very important principle, and it can lead to stunning conclusions if you can figure out how to, creatively decide what are your pigeons and how to creatively decide what are your pigeonholes. And if there are more pigeons than pigeonholes, then, there are at least 2 or more pigeons in a pigeonhole. And then that's an existence argument. So it shows that there exist 2 or more pigeons in the pigeonhole. And, that shows that something exists, 2 or more pigeons. And if those 2 pigeons match in some property, then you've just proved that there exists 2 or more things that match in that property. Okay, whatever it is, whether it was social twins or matching subsets, and we did some examples last time. Okay. Now, today, probability. Probability is related to counting. You can think of counting as sort of, the hard size of a set. And you can think of probability as some kind of a soft size of the set. Anyway, but let's not philosophize too much. We're going to focus on the mechanics of probability, so we'll spend a lot of time today talking about how to compute probabilities and do a bunch of examples. Okay. And then discuss a little bit of the sort of mathematical foundations of probability. The mathematical foundations of probability lie within the mathematical foundations of sets. So we'll talk about probability and sets. And then we'll discuss, certain situations where computing probabilities can be much easier than the general case. And these are sort of uniform probability spaces where things are uniformly distributed. At the end, I'll touch on the concept of infinite probability spaces. So in the context of discrete probability spaces. Okay. And so let's begin. You've probably heard on the radio or the weather channel that the chance of rain tomorrow is 40%. And have you ever stopped to think, what exactly does that mean? Because tomorrow it's either going to rain or it's not going to rain. So what's this business of 40%? Okay, so let's sort of try to interpret this statement a little, and that's the extent to which we're going to philosophize about probability. Now, there's the sort of subjective degree of belief approach, which says my degree of belief, my level of certainty for rain tomorrow is 40%. Okay, that's a little bit too soft for my liking, and it's very vague, and I don't really know what that actually means, subjective degree of belief. Okay, there's another sort of quantitative view which says, this 40% is related to the quantity of rain. Imagine it could rain 0 up to 100 milliliters up to 100 millimeters of rain tomorrow. So 40% roughly sounds like we'll get about 40 millimeters. That's what I'm saying. That's also not quite accurate. So what it's sort of intending to convey, okay, is sort of a more practical, more objective view of the world. Where imagine, okay, if we repeated tomorrow 100 times. Did I say more practical view? Well, let's just play along a little, okay, because we're just trying to interpret this statement. Imagine if you could repeat tomorrow 100 times, then on 40 of those days it's gonna rain. That's what that sentence is saying. That's the frequentist view. And that's the view we're going to take, the sort of operational, the practical, the objective view. Now, of course, it's not easy for us to repeat tomorrow 100 times. So we have to take that view with a grain of salt, or we have to consider experiments that are repeatable, where this argument sort of makes sense. Okay? And so let's consider coins. So someone gives you a fair coin. What does that mean? We could say that the chances are 50% that the fair coin will flip heads. And now we can repeat the following experiment. Flip the coin. Okay, so flip it 100 times. And what this sentence says is that on 50 of those flips, or roughly speaking 50 of those flips, you're going to get a heads. Okay? So this is this frequentist view, and that's the view that we're going to be taking. That's the view that's sort of appropriate to the computational side, the mechanical side of probability, which is what we're going to be focusing on. How do we compute probabilities, and what good are they? What can we use them to do? Okay? And probability is used in all kinds of fields today: economics, physics, computer science, biology, statistics, and so on and so forth. It's all over the place. Okay? So, let's think about some other experiments, okay, having to do with fair coins, and I'll just pose these questions, and then we will see where they lead us. Okay. So, the first question: you toss a fair coin 3 times. Okay. How many heads will you get? Well, that's related to this 50%. But now let's think about this. You toss a fair coin 3 times, and this 50% says I should get 1.5 heads. Okay, so that's a little weird. Right? So you toss a fair coin 3 times, how many heads will you get? Okay, think about that question. Here's another question for you to think about. You toss a coin, and you keep tossing a coin until you get a head. Okay, so it's related. It's related to coins. Okay, and we like coins because we can do things with coins repeatedly, like flip them. Okay, you toss a coin and you keep flipping until you get a heads. How many tosses will you make? Okay, so think about this. Let's just think about what are the answers to these two questions. So if we try to literally interpret the 50% because they're fair coins, the coin that's flipped 3 times, we are expecting to get 1.5 heads. No, that's not possible. Okay, not possible. Okay, you'll get either 0, 1, 2, or 3 heads when you flip it 3 times. Okay, and how many times do you have to will you make a coin flip until you get a head? Okay, so the fundamental thing that you should take away from these two relatively simple everyday questions is there's no answer. Okay, and that's the idea behind probability. That's the idea behind randomness. There's no answer. The outcome is uncertain. And you won't know the outcome until you actually do the experiment. So until you actually toss the coin 3 times, you won't know how many heads you will get. Okay? And until you toss the coin, and until you run experiment 2 where you toss a coin until you get a head, you won't know how many tosses you make. Okay? Now, but nevertheless, we would like to sort of think about and analyze these 2 experiments before we actually go and do them. For example, do I want to do the experiments? I need a way to analyze these experiments, and probability handles such settings. Okay? It's this beautiful mathematics that can handle such settings where you don't know the outcome is uncertain. Okay, now for some history. Let me tell you a little bit about the birth of mathematical probability, and it's an interesting story. Okay, so there's an interesting character, Antoine Gombeau, Chevalier de Mer, and he's a gambler, and in his wheeling and dealing, he wants to know, should I bet even money on at least 1 double 6 in 24 rolls of a pair of dice. Okay, so you roll the pair of dice 24 times, and if a double 6 appears, you win. Okay, is it worth even money? He also had the question, what about at least 1 6 in 4 rolls of a die? Okay, so you roll the die 4 times, if a 6 appears, you win. Is that worth even money? Now, he's just a gambler, he's no mathematician, so he calls upon the great Blaise Pascal. Now Pascal, remember Pascal's triangle? So the great Blaise Pascal, and asks, what should I do? Should I bet even money on these gambles? Pascal thinks, this is an interesting question. Let's bring in the other great giant, this big, huge giant, Pierre de Fermat. And you may have heard of Fermat's last theorem. Okay, Fermat was a great mathematician. So Fermat gets into this conversation, and there's this correspondence that's been ignited between Pascal and Fermat, and this correspondence is what ignited the birth of mathematical probability. And today, it's this very formal, mathematical, very rigorous discipline that can be used to analyze the real world, randomness in the real world, randomness in algorithms. But it all started with a question about a very simple gamble. See if you can answer this question. Meanwhile, we are going to start simpler and work our way through computing probabilities. So let's move to the board. Okay, probability. Now, probability can be a little bit counterintuitive, especially if this is the first time you're seeing it. So, our goal is to start by building the tools for mechanically computing probabilities. Okay, and then we will, interpret these probabilities as we go along. Okay, so hopefully, how to compute them and what they mean will sort of become clear, together as we sort of compute various probabilities for various outcomes. Okay, so now the fundamental thing to remember here is that, probability is relevant when you're doing some experiment and the outcome is unknown, it's uncertain, it's, random in some sense. Okay, so let's consider one such experiment. Okay, so flip 2 coins, okay, and you win if the coins match. And the key here is you're going to flip the coins randomly. Okay, so flip 2 coins randomly, and you win if both match. Okay, now here's an experiment for you to do at home. Repeat this experiment 1,000 times. Okay, repeat 1,000 times. Okay, and see how many times did you win, and see how many times did you win. Okay, repeat 1,000 times and see how many times did you win. And my bet is that you will win approximately 500 times. Okay, approximately 500 times. Okay, Now, you can do this experiment at home, get a couple of coins, and flip them both 1,000 times and see how often they match, and then you count up how many times you won. Now, of course, we're computer scientists, so we can try to do this experiment 1,000 times, in the computer. Okay, and you can do this if you're familiar, or you can look up on the internet. All programming languages, all programming platforms have a tool for randomizing, what's called randomizing. So if you want to pick two outcomes, let's say 0 and 1, or heads and tails, you want to pick one of those randomly, okay, i.e. with equal probability, just like what we talked about with 50% chance of picking one and 50% chance of picking the other. So, most programming platforms have a randomizing device, sometimes called RAND. Okay, so you can run this experiment either physically or write a little program to do this and just count up how many times you won. Okay, now what we're going to do is we're going to try to, develop a machinery that would come up with this number approximately 500 times without actually doing the experiment. Okay, and here's the way it goes. Well, the first step, okay, before you sort of invoke the machinery of, computing a probability, is to realize that the outcome is random. Okay, so step 1, realize the outcome is random. Okay, and so in this case, that is clearly true. Okay, because who are you going to win or are you going to lose? We don't know until we do the experiment. So it's a random outcome. Okay, and then when you do the experiment, it's not always the case that you will win or always the case that you will lose. Sometimes you might win, the coins will match. Sometimes you might lose, the coins will mismatch. Okay, and so that's what we mean by the outcome of, you realize that the outcome is random / uncertain. Okay, and the outcome of what? The outcome of the experiment that you're trying to do or analyze. The outcome of what? Of an experiment, that you're trying to do or analyze. Okay? Okay. So the next step, okay, when you don't know what the outcome is, but it is certainly possible that you will know all the possible outcomes. Okay, so figure out all the possible outcomes. So in this case, when you toss two coins, figure out all the possible outcomes. So first step, second step, figure out all possible outcomes. Okay, now there are many useful sort of aids, tools, devices that you can use to figure out all the possible outcomes. Okay, and this goes back to what we've just been discussing, which is counting. Okay, so figuring out all the possible outcomes is very similar to figuring out the number of possible outcomes, the number of ways that you can toss two coins. Okay, and essentially, the way to sort of figure out all the possible outcomes is just an extension of the product rule. So the product rule tells you how to count the possible outcomes, how to figure out all the possible outcomes. Remember that you're doing something and there are, let's say you're choosing a way to do x1, then a way to do x2, then a way to do x3, and so on. And if the number of ways are n1, n2, n3, and so on, then the total number of outcomes is the product. And when we were counting, we were only interested in the total number of outcomes. But now that we're doing probability, we're interested in the actual outcomes. So you can't just tell me that the number of ways of doing, x1, the thing x1 is n1. You have to actually show me those outcomes. Okay? And then for each of the possible outcomes for x1, the number of ways of doing the second thing are n2. Well, you have to show me those outcomes. Okay, and remember when we were doing the shirts and the ties, I represented that on a tree. So a tree is often a very convenient way for sort of figuring out all the possible outcomes. Okay, sometimes we use a grid, sometimes a tree. I mean, there are many sort of aids and tools and devices for figuring out all the possible outcomes, but that's usually the first main step in computing a probability, is to figure out all the possible outcomes. Okay? After you realize that you're analyzing an experiment whose outcome is uncertain, is random. Okay, so in this experiment, just like picking a shirt and then picking my tie, we're flipping two coins. Okay, and so it's convenient to sort of represent these outcomes on a tree. Okay, sometimes we call this the outcome tree. Okay, so figure out all possible outcomes, and I'll put in parentheses a very useful aid in figuring out all possible outcomes is what we call the outcome tree. Okay. So you start at the root of a tree. Okay? Which is, think of that as the beginning of the experiment. And now, what's the first thing you do in this experiment? Well, you toss the first coin. Okay? And there are two possible outcomes. Okay? So the first coin can either be heads or tails. Okay? Now, for each of these possible outcomes, what can happen next? Okay? So if the first coin is heads, you toss the second coin, you flip the second coin, and its outcome can be either heads or tails. Okay? Heads or tails. Okay, what about if the first outcome was tails? Same thing. You flip the second coin, and its outcome can be either heads or tails. Okay, and so we call this the tree, for the experiment, or the outcome tree for the experiment. But, think back to the product rule when we talked about counting, and when we were interested in the number of possible outcomes, we just did 2 times 2. So n1, number of possible outcomes for experiment 1, n1 equals 2, and in this case, the number of possible outcomes for experiment 2, for the second flip, after you have done the first flip, okay, is 2. So n2 equals 2. And so the total number of outcomes, when we were doing counting, the total number of outcomes is the product gives 2 times 2 equals 4 total outcomes. Okay, and we see them here. So you've got heads, so we'll label that outcome heads. You've got heads, tails, we'll label this outcome heads, tails. You've got tails, heads, we will label this outcome tails, heads. And you've got tails, tails, we will label this outcome tails, tails. Okay. And this method that I'm describing for constructing all the possible outcomes, you can always fall back on this method when things get a little hazy. Okay. Now, and if when we were counting, we were just interested in the number of outcomes, but now that we're doing probability, okay, we list all the outcomes. Okay. Now, it's the tree and the method of getting to these outcomes is not so important. What's important is that we got to these outcomes. Okay. Now, when we talk about probability and sets, what we will say is that for each outcome, you need to assign a probability. Okay. So for each outcome, you need to assign a probability. Okay. So for each outcome, you need to assign a probability. Okay, and once you have assigned probabilities for these outcomes, that's all that matters, and we can run the machinery of probability theory. But now what I'm going to do is I'm going to spend a little bit of time telling you how do we assign probabilities to the outcomes for most of the experiments that we are interested in performing in practice. Okay. Now, in theory, you can assign any probabilities you want here, and you have defined, a mathematical object, which is a set of outcomes with a set of probabilities. But for almost anything we do in practice, there's an associated, sequence of steps that take place. Okay, and in each step, you can represent each step by, a branching of, of a node in a tree. So the root node is the first step, and it branches into the 2 possible outcomes. Then the second node here is, what happens in the event of a head, you branch off. What happens in the event of a tail, you branch off. So trees are very good ways of representing the sort of sequence of events that can happen in practice, okay, when you run an experiment. Because whatever you do in practice, you have to do it sequentially. Step 1, step 2, step 3, step 4, step 5. And it's ideal to represent that on a tree. Okay, and just like in this case. Okay, and then when you have these kinds of experiments that you do, it's typically the case that each step in your experiment results in partial outcomes. Okay, so you can think of heads as a partial outcome of this experiment, and then when you do the second step, you go heads, and now you've got the full outcome, and you can even assign probabilities to these partial outcomes. Okay, and this is where the mechanical probability comes into play. Okay, so one thing I want to mention before we continue, that you might say, well, you've got heads, tails, so heads, tails, so that's the first coin came up heads, and the second coin came up tails, and then you got tails, heads, and so the first coin came up tails, and the second coin came up heads. And you might say, but aren't these the same outcome? You got 1 heads and 1 tails. Well, they are effectively the same outcome if all you care about is the set of, flips. But sometimes you might care about the sequence. So this outcome and this outcome are different outcomes, and that becomes important when it comes time to assign probabilities. Okay, so let's start at the first partial outcome, and we will ask, well, what's the probability of coming to this heads, and what's the probability of coming to this tails? Essentially, we are saying we need to assign a probability to this edge and a probability to this edge. Okay, and the probability to this edge, now it depends on how you flip the coin, and this is where the term randomly comes in. Okay. Now, typically when we say randomly, we mean that each of your choices is equally likely. So in this case, we have, two choices. Okay, so randomly means each choice is equally likely. Okay, and so one thing that you need to know about probabilities, and this is part of the mathematics of our mechanical probability setup, is probabilities add up to 1. So it's 50% chance of rain tomorrow and 50% chance of sun tomorrow. Okay, so 50 plus 50, 100%. So something must happen tomorrow. So when we represent probabilities using sort of percents, or actually we're going to use numbers between 0 and 1, those numbers must add up to 1. Okay. And so since these two outcomes are equally likely, that's what flip a coin randomly means. Okay. And you can think of a coin as a randomizing device that chooses equally likely, that chooses one out of two equally likely outcomes. Okay, and you can think of k-sided dice or k-sided coins, or actually running in your computer, we've got a randomizing device, RAND. Okay, and so if each of these two outcomes are equally likely, and those are the only outcomes that can occur, then their probabilities are 1/2 and 1/2. Okay, because the two probabilities, so you can think of 1/2 as 50%. 50% of the time you get heads, 50% of the time you get tails. 50% is we use 1/2 to represent 50%, 1/2 to represent 50%. 1/2 plus 1/2 is 1. So these are the only two equal numbers that are between 0 and 1 that add up to 1. Okay, and now, so you can interpret this as saying, when I start this experiment, half the time I will go down this branch, half the time I will go down this branch, 50% of the time I will go down this branch, 50%. So with probability 1/2, we go down this branch. With probability 1/2, we go down this branch. Okay, so that's the way this would be read. And we can say that, okay, we've analyzed the first step of the experiment. Now, if this happens, it's the same experiment again with the second coin. So 1/2 of the time we'll go down this branch, and 1/2 of the time we'll go down that branch. Because again, we're tossing a coin, a fair coin, randomly. Fair coin randomly means equal probability for both outcomes. And the same thing here. If you had gotten tails, which is half the time, half of that time, so half the time once you're here, half the time you'll go down this branch and flip a second heads, half the time you'll go down this branch and flip a second tails. Okay, now, this is the product rule for computing probabilities. Okay, so if I want to compute the probability of this outcome, now this has to do with conditional probabilities. What we say is that the probability of getting this head, assuming that you have fixed this outcome and gotten here, is 1/2. Okay, so the probability to get here is 1/2, and the probability to go from here to here is 1/2. And so we say that the probability to go from the root, the start of the experiment, to this leaf, okay, which is the end of the experiment, is the product of the probabilities for that path that you have to travel. So product rule, okay, computes, okay, so let me write it here. Use product rule to compute probabilities of outcomes. Okay, so for each outcome you need to assign a probability. That's what we're addressing here. So use the product rule to compute the probabilities of outcomes. So the product rule here says 1/2 times 1/2, 1/4. 1/2 times 1/2, 1/4. Okay, 1/2 times 1/2, 1/4. 1/2 times 1/2, 1/4. Okay, good. Okay, so I'm just giving you a specific arithmetic, a specific way to compute probabilities for these outcomes. You can't argue with that. It's a way to compute probabilities. The only question is this way of computing these probabilities, does it have any meaning? Does it have any link to reality? Is it useful in any way? Okay, and now, and we will see. So let's now pause a little bit and try to interpret this. Okay, so what this is saying is that, so let's sort of interpret this and sort of try to make sense of it. So what this is saying is that, when you do this experiment, okay, half of the time you will go down this branch, which is you will pick heads. Okay, and then of that half of the time, a half of that will come down this second branch. So a half of the half, okay, results in arriving at this leaf node of your tree, this end of the experiment. Okay. So a half of a half is exactly a half times a half, which is 1/4. That's the sort of intuition behind the product rule. Okay. And what this says is that, if you let's say you flipped 1,000 times. Now we'll give an interpretation of this 1/4. Let's say you flipped 1,000 times. You flipped 1,000 times. How many of those times will go down this branch? Well, half of them. Okay. So I hope you said 500 approximately, because things are random. So approximately 500 will go down this branch. Approximately 500 will go down this branch. Okay. And then of these 500, how many go down this branch? 250. Because a half of those. And how many will go down this branch? 250. And how many go down this branch? 250. How many go down this branch? Of these 500, half of them, 250. So when you run this experiment 1,000 times, 250 times you will end up here. So 250 times you will end up here, 250 times you will end up here, 250, 250. Okay, nice. Okay, and notice that 250 is 1/4 of 1,000. Okay. And so using this method for computing probabilities gives us the way to sort of interpret these outcome probabilities. So the probability of an outcome, okay, is approximately, well, this is a number that we can compute, but if you did this experiment in practice many times, for example 1,000 times, the probability of this outcome is approximately going to equal, now this is a number, but when you do the experiment, it's approximately going to be equal to the number of times you see the outcome divided by the number of times you run the experiment. Okay, and that is exactly the frequency interpretation of a probability. It says that the probability of some outcome is the frequency of times you will observe that outcome when you do the experiment. And this, of course, assumes the experiment is repeatable. Okay? So we can only do the experiment when the experiment is repeatable, for example, flipping 2 coins. But this probability of an outcome still has that same interpretation, even if the experiment is not repeatable, such as the chance of rain tomorrow is 40%. Okay? So it still has that interpretation, even if the experiment is not repeatable. Okay, so I've sort of illustrated how you get to these outcome probabilities, and we've talked about a little bit about the interpretation of these probabilities. Now let's summarize this into two rules, okay, that end up with, for each outcome you need to assign a probability. Okay, so the first, let's call it step number 3. Okay, is you need to sort of compute probabilities for each partial outcome. Okay, or you need to assign probabilities to each of these edges. So assign probabilities to each edge. Okay, and step 4, for each outcome you need to assign a probability, i.e. the probability of an outcome is equal to the product of probabilities on the path to the outcome. Okay, so So for each outcome, you need to assign a probability, and so how do you do that? You take the product of probabilities on the path to the outcome. So the path to this outcome is, h, and so the product of those is 1/2 times 1/2, which is 1/4. Okay. So couple of notes, observations. First, the root of this outcome tree is the start of the experiment. Okay. Well, the end of the experiment are always leaves of the outcome tree. Okay. And now I will just mention that it looks like this outcome tree is always branching into 2, okay, and then into 2 here, okay, and then 2 here. So a couple of things that will become clear in some of the examples we do. You don't always have to branch into 2. So this is the case for flipping a coin, where the number of outcomes in each stage of the experiment is 2. Okay, and then you moved from the start of the experiment to heads here, the start of the experiments to tails here. Okay, and you could think of a more complex experiment where if you get heads, flip a coin. If you get tails, roll a die. Okay. If you get heads, flip a coin, that gives you a branching into 2, because the coin can be heads or tails. If you get tails, roll a die, that will give you a branching here into 6, if it's a standard 6-sided die. Okay. And you can think, what would be the edge probabilities in that case? They would all be 1/6. Okay. But let's not get into those complications. I just want to mention that don't get fixated on the specific shape of this outcome tree. Okay. Points to note. Okay. The start of the experiment is the root. Every step in the experiment results in a branching from nodes, and the end of an experiment are the leaves, okay, which we call the outcomes. Okay, and now we've assigned probabilities to each edge, okay, i.e., if, so as an example, okay, now in theory you could assign probabilities arbitrarily. If the coin was not fair, if it wasn't a random flip of a fair coin, maybe it's a biased coin. So maybe 2/3 of the time it comes up heads, and 1/3 of the time it comes up tail. But randomly, so typically if we choose among our options randomly, random choice among k outcomes means that the probabilities for each of those outcomes, so the probabilities along those edges, is 1/k. Implies edge probability 1/k. Okay, so okay, so what? Okay, so we've done all this. Fantastic. What the heck? So who cares? Now we've gotten probabilities. Okay, and we've gotten to the point where we've gotten probabilities, and we've gotten to the point where we've even interpreted the probabilities of each outcome. But we want to know how often, what are the chances that you will win? Okay, and so that's the next step. You ask a question. So step 5. You ask a question. Okay, so in this case, so you can think of this whole process, steps 1, 2, 3, and 4, as preparation. Okay, you've sort of set up the experiment in this formal way with steps. Step 1, step 2, and so on, and you've identified all your possible outcomes, and now you've assigned outcome probabilities. Now, in theory, we can do probability theory just from here. Okay? But it is helpful to know how we got to our outcomes and what are their probabilities. Okay, and now we're going to ask a question. Okay, so what's the question? Well, you win if both coins match. You win if both coins match. Okay, so when do you win? Okay, so when do you win? Okay, now you ask this question, okay, and so when do you win? That identifies a set of outcomes that correspond to this answer. Okay, that this identifies a set of outcomes. Okay. So in this case, it identifies a set of outcomes that correspond to the answer to this question, which answer the question. Okay. So let's see, what are those outcomes? When do you win? Okay. So you win when both coins match. So when do you win? Let's highlight them. When do you win? Here, both coins match. And here, both coins match. Okay, so that identifies a set of outcomes which sort of answer the question. So it's identified the set of outcomes, HH and TT, along with their outcome probabilities, 1/4, 1/4. Okay. That set of outcomes, and this is a formal definition of what's called an event. An event is any set of outcomes, any subset of all the outcomes. Okay, but we are not interested in just any old event. We are interested in the set of outcomes that answer my question. So this we will call the event that is of interest to us. So this is the event of interest. Okay, so that's step 5. So step 5, we could have equally said, instead of ask a question, which then leads us to the event of interest, we could have just said abstractly, identify the event of interest. Well, it's more interesting. It's sort of more intuitive to approach this from what's the question I'd like to have answered. And okay, for that question, what is the subset of outcomes that answer that question? Okay, and we have identified that here. And then step 6, you answer the following question: what's the probability that this question that you asked is going to occur? So when do you win? You win when this happens. How often do you win? What are the chances that you win? So that's where probability comes in. Okay. So how often do you win? Okay. Effectively, we're saying what's the probability of this event? That's the answer to that question. What is the probability of this event that answers the question? Okay, now formal definition. The probability of that event is just the sum of the outcome probabilities in that event. So we'll say that the probability of the event of interest, the event, script E, is equal to the sum of outcome probabilities, which is equal to 1/4 plus 1/4, which is 1/2. Okay. And that's the end of the calculation. Okay, now let's interpret that. What is it saying? So you can interpret this as saying, what's the probability? How often, in terms of frequency, how often does an outcome in my event of interest, which answers the question I was interested in, so how often does an outcome in my event of interest occur? Half the time, 50%. Okay? And so now we can go back and sort of answer the question, if I did it 1,000 times, roughly half of the time, I'm going to get an outcome in my event of interest, which answers the question I'm interested in. And so that's approximately 500, and that's where I got that 500. Okay? And we can look at it also from this perspective. I win in this red box or that red box, and we just analyze that, this red box occurs 250 times, approximately this red box occurs 250 times. That's the frequency interpretation of probability. So in all, this happens 500 times. And that's what that probability answers. Okay? So this is, so by the way, this is just a very purely mechanical approach to computing a number. Okay? And that number has an interpretation as, how often does the thing you are interested in occur? Okay, how often does the thing you're interested in occur? What was the thing we were interested in? Winning. When do you win? When the coins match. So how often do the coins match? So let me summarize this entire mechanical procedure. And the fact that it has the interpretation as, how often does if you repeated the experiment, how often will the thing you're interested in occur is what makes probability theory so useful in the real world. It allows us to reason about what will happen in a random probabilistic experiment without actually having to do the experiment 1,000 times. And doing an experiment 1,000 times can either be very costly, time-consuming, or even impossible if we're talking about predicting the weather tomorrow. Okay, so summary. Mechanical approach to computing probabilities. Step 1, you need to sort of have an idea what's the experiment you're doing. Okay. And is the outcome random or uncertain? If yes, then figure out all the possible outcomes. Okay? And the outcome tree, the tree of possible things that can happen in your experiment as the experiment unfolds, is a very useful device for computing all the possible outcomes. Once you have computed all the possible outcomes, you need to assign probabilities to each outcome, and that effectively amounts to, for each outcome, multiply the probabilities in each stage of the experiment, which mechanically becomes multiply the probabilities for each edge in your experiment. That leads to this outcome, which is a leaf of the outcome tree. Okay? So assign the edge probabilities and then multiply edge probabilities to get outcome probabilities. Actually, once we have outcome probabilities, we're done with everything else. Okay? And so sometimes probability theory starts by saying, you have a bunch of outcomes, okay, and each of these outcomes has a probability. Boom, and these probabilities are non-negative and they sum to 1. Boom, done. But that's very hard to get a grip on intuitively. It's more intuitive to think about an experiment that naturally leads to the outcomes, and then the probabilities of those outcomes are sort of are interpretable as how often each of the outcomes occurs, which then leads to this, figure out how often each step of the outcome occurs, okay, and then multiply those. 1/2 of 1/2 give me 1/4, okay? So once we have outcomes and outcome probabilities, we're done with setting up the experiment. We now go and ask a question. What are you interested in? What do you want to know? Okay. And whatever it is that you want to know, you should be able to then sort of massage it into a subset of the outcomes that if one of these outcomes occurs, it more or less answers your question. It satisfies whatever you're interested in. In this case, we're interested in when do we win. We win when the outcome is head-head or tail-tail. Okay. And once you have this event of interest, to compute how often this thing you're interested in occurs, you just add up the event probabilities. That's the 6th step in this mechanical route to computing this number 1/2. And then you interpret this 1/2 as if you were to repeat the experiment, how often would it happen? Okay, so the mechanical approach to computing probabilities. Now let's erase and do lots of examples. Okay, examples and practice. Let's start with a practice exercise. So practice exercise. Okay, so you roll a pair of dice. You roll 2 dice, and there's a first roll and a second roll, and you win if the first roll is less than the second roll. Okay, so roll 2 dice and win if first roll is less than second roll. Okay. And so then the question is, what are your chances of winning? So use this mechanical approach we discussed to compute the probability to win. Probability to win equals. Okay, so I'll give you a couple of seconds. Pause the video. 1, 2, 3, 4, 5. Okay, now if you're coming back and you computed the probability as 5/12, fantastic. You've mastered this mechanical approach to computing probabilities. If you're here just for the ride, well, the first roll in a pair of dice rolls is less than the second with probability 5/12. If you didn't get that, then look up the exercise in the book, see how we solved it, see what you did wrong, and try to get as much practice as you can, because probability is very counterintuitive. Okay? And we're going to do a couple of examples which illustrate how counterintuitive probability is. Okay? We're going to start with a game show that was called Let's Make a Deal. Okay, it aired in the 60s, 70s, and 80s. Okay, and it involves a host, Monty Hall, so sometimes it's called the Monty Hall problem, and a column in the New York Times called Ask Marilyn, okay? And we'll see how all these things tie in together when I tell you about the game. So, the game concerns 3 doors. So there are 3 doors. Let's label them door 1, door 2, and door 3, okay? And the game proceeds. The game show proceeds as follows. There's the contestant, and the contestant stands in front of door 1. So the contestant in front of door 1. Okay. Now the game proceeds as follows. A prize is placed randomly behind one of the doors. Okay. Prize placed randomly behind a door. So the prize could be either behind door 1, 2, or 3. Okay? Now this is where it gets tricky. Now, the host, Monty, will come and open one of the other doors, not the door the contestant is in front of. Will open one of the other doors, and it must be the case that the prize is not behind one of the other doors that are opened. So the door that's opened will not contain a prize. So Monty opens a door with no prize. Now in the game, I believe the doors with no prize had goats. Okay, so 2 goats and 1 prize, and the goal of the contestant is obviously to get the prize, because you can't really do much with a goat these days. Okay. Now you might ask, what happens if the prize is behind door 1? Then Monty has a choice of doors to open, okay, and he picks randomly. Okay. Now let's imagine that Monty opens door, let's say door 3. Okay, so now Monty gives the contestant a choice, because door 3 has a goat. So there are 2 options for where the prize can be, and Monty asks the contestant, do you want to switch? And now, very often on the show, the contestant looks at Monty, very suspiciously, thinking that Monty is trying to get the contestant to switch, to sort of, move the contestant away from the prize that is behind door 1. And many contestants don't switch. So someone wrote into Marilyn's column, asked Marilyn and asked her, Marilyn was savant, supposedly the person with a very, very, very high or highest intelligence, should I switch or not? That was the question posed to Marilyn, and Marilyn said in the column, you should switch, and it's twice as likely for you to win if you switch. And then there was a huge, set of responses, even by mathematicians who said, this is all nonsense, you're failing to educate the public correctly. Look, there are clearly 2 doors, and your chances are 1 in 2 if you stay, and 1 in 2 if you switch, and so it doesn't matter whether you switch or not. So let's analyze this game, and we'll prove that Marilyn was right, and everyone else who disagreed was wrong. Okay, so here's how we're going to prove it. And we're just going to use our mechanical, framework for computing probabilities. So the start of the experiment has the contestant behind door 1. Okay, and now the prize is placed behind one of the doors randomly. So the first step is we have to consider all possible outcomes. Okay, so what are the outcomes? The prize can be either behind door 1, or behind door 2, or behind door 3. Okay. Now, once the position of the prize is chosen, now the next step in the game takes place, and Monty opens a door which has no prize. So if the prize is behind door 1, Monty has a choice of which doors to open. So Monty can open either door 2 or door 3. Okay? And if the prize is behind door 2, then Monty has no choice, because Monty has to open a door that has no prize, so he has to open door 3. So he has to open door 3. So this you can think of, where's the prize? Okay, and this you can think of as, what does Monty do? Monty opens. Okay, and if the prize is behind door 3, contestant is in front of door 1, so Monty has to open door 2. So this is interesting. So if the prize is behind door 1, there are 2 possible ways in which the experiment can continue. But if the prize is behind door 2 or door 3, there's only one possible way in which the experiment can continue. Now we can label these, leaves, these final outcomes as door 1, prize behind door 1, Monty opens door 2. So we can label this 1, 2. Behind door 1, open door 3, 1, 3. Behind door 2, open door 3, 2, 3. Behind door 3, open door 2, 3, 2. Okay, so these are the possible outcomes. Possible, and if we asked you to compute the number of possible outcomes, there are 4. Okay, but now when we're computing probabilities, we need to compute the probabilities of the outcomes. Okay, and to do so, we compute the probabilities of each partial outcome and each outcome from each partial outcome and so on by adding edge probabilities. So these edges, because you choose randomly from among 3 choices, okay, the edge probabilities are 1/3. Okay, here you choose randomly from among 2 choices. Okay, so half of the time you go this way, half of the time you go that way. This corresponds to 1/3 of the time, 1/3 of the time, 1/3 of the time. So 1/2 of the time, 1/2 of the time. And here, all the time, if you get to this point where the prize is behind door 2, all the time the door 3 is open. So all the time corresponds to a probability of 1. Okay, and here all the time door 2 is open. So all the time corresponds to a probability of 1. Okay, so now we compute outcome probabilities, which correspond to what fraction of the time does this outcome occur. It's half the time of 1/3 of the time. So that's where we multiply 1/2 times 1/3. So we get 1/6. Okay, half the time of 1/3 of the time, multiply 1/6. Okay, 1 all the time of 1/3, so 1/3. 1 times 1/3, 1 times 1/3. Okay. You can interpret this as 1/6 of the time. When you run this experiment, the outcome will be prize behind door 1, Monty opens door 2, host opens door 2. Okay, and so this is the mechanical probabilistic specification of the experiment, where what's important are the outcomes and their associated probabilities. Now we ask our question. Okay. And what's our question? Okay. What are our chances of winning if we switch? Chances of winning if we switch. Okay, question mark. Okay. So we go back to our outcomes and look at in which outcomes do we win by switching. So if the prize is behind door 1, you cannot win by switching. You lose by switching. If the prize is behind door 2, then you'll switch to door 3 and win. If the prize is behind door 3, then you'll switch to door 2 and win. So in these outcomes, you win by switching. Okay? And that's the key. We ask a question and then we identify the outcomes which correspond to that question. And in this case, we define the event of interest. The event is the outcomes 2, 3 and 3, 2. So I want to emphasize that the event or the event of interest is a subset of all the outcomes. It's a set of outcomes. Now we can compute the probability for this event occurring, which corresponds to the probability to win if you switch. So the probability of the event occurring is the probability to win if you switch. Okay, so now this big P means probability. And we just add up the probabilities in each outcome. So this has a probability 1/3. This has a probability 1/3. Okay. And so you get 1/3 plus 1/3, which is 2/3. Okay. The probability to win by staying is the opposite outcomes, the complement outcomes. Okay. And the complement outcomes have some 1/3. So the probability to win by staying is equal to 1/6 plus 1/6, which is 1/3. Now we could have figured that out by actually looking at the answer we already got. You win if you switch with probability 2/3. Okay, so you win by doing the opposite, the complement, okay, with probability 1 minus of that, because the probabilities must add up to 1. You either win by switching or you win by staying. So the total sum has to be 100%, i.e. the probability to win by staying has to be 1 minus of this, which is 1/3. No surprise. Okay, now why did this cause so much contention? Because the intuitive argument is, well, you have two choices, okay? And so if you stay, your chances are 1 in 2, and if you switch, your chances are 1 in 2. The point is that this second choice, this other door that the host didn't open, is more likely to contain the prize than the door that you are behind. And sort of one way to view that is, you have 3 doors, door 1, door 2, door 3, okay? And the prize is equally likely to be behind each door, okay? And the strategy of winning by switching wins whenever the prize is behind one of these doors. Either of those doors works for winning by switching. And there are 2 out of 3 doors that you can win by switching. And so the chances are 2 out of 3 doors to win by switching. And that's just because the prize is placed has equal chances to be behind each door. Okay? And the way the game is structured is such that if you switch, you basically win whenever the prize is behind door 2 or door 3. Because Monty will have to pinpoint that to you by opening the other door. So you win whenever the prize is behind door 2 or door 3. And that happens 2 out of 3 times. You win by staying only when the prize is behind door 1, which is 1 out of 3 times. Okay? So if you want to perform an intuitive analysis, this is the correct intuitive analysis. Okay, but like I said, probability is very counterintuitive. So it's always safest to go to to go through the full mechanical route and get the answer. Okay, and now we're going to see something really strange. Okay, and that underlines why it's very important to always use the mechanical route to compute probability. So what is this thing that's really strange? Okay, so I want to show you that when games involve chance and probability, it's possible that you will prefer one game, okay, to another. You will prefer another game to a third, and then you will prefer the third game to the first. So it's kind of like a non-transitive behavior. And let me illustrate with dice. Okay, so this is I'm gonna call this non-transitive dice. Okay, so non-transitive dice. Okay, and we'll do this example carefully. Okay, and you can think of this as, a game that you could play with your roommate friend who's a history major and make lots of money off them. Okay, and here's how the game goes. Okay, so I'm going to give you 3 dice. They're 3-sided dice. Okay, so die A, die B, and die C. Okay. And maybe if we were in the live version of the class, if you had answered some question correctly, I might have even given you some of these dice. Okay. So die A, it has 3 faces, so it's a 3-sided dice, and the faces are, if I draw the dice 2, 6, and 7. Okay, so think of 3 die faces. So this is 2, that's 2, 6, and 7. Okay. And die B similarly has 3 die faces. 1, 5, and 9. Okay, so that's die B, 1, 5, and 9. And die C has also 3 die faces. Okay, and the faces are 3, 4, and 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 3, 4, and 8. Okay, so you might wonder, well, okay, good. First thing you might be wondering is, how do you construct a die with 3 faces? Well, you can take a sphere and chop off 3 parts, and whenever you roll it, it's equally likely to land on each part. Or, more simply, you take a standard 6-sided die and just add, and replicate the faces. Okay. So now in a standard 6-sided die, you could replicate the faces and have 2 faces with 2 dots, 2 faces with 6 dots, and 2 faces with 7 dots. Okay. So that's one easy way to create a die with 3 faces. But okay, so for the moment we have 3-faced dies. So here's what you can do. You can take a friend and you can say, here's the game we're going to play. You pick a die, whatever die you want, and I pick a die, okay, and then we roll, and whoever gets the higher number wins. And your friend, because your friend is a history major, is never going to trust you and say, no way, I'm not playing. You know too much probability for me. So you say, well, listen, we can play this game for a while, and if you think that I have the better dice, okay, then you can switch any number of times. So we'll play the number of times. Okay, you can switch any number of times. And so the friend now looks at you and says, okay, that sounds reasonable, because if I can't analyze probability, but I can see what die you picked, and then, we'll play a few times. If I'm losing, I'll pick your die. I'll switch dies with you. Okay, and so let's analyze this game, and I'm going to show you something very counterintuitive that can happen when you do probabilistic analyses. Okay, it's not like deterministically, if I can beat you and you can beat John, then I can beat John. Okay, that's sort of like how things are with, let's say, tennis. But even in a game like tennis, that may not be the case, because I know how to exploit, your weakness, and you know how to exploit John's weakness, but you don't know how to exploit my weakness. But John knows how to exploit my weakness. So even, games like tennis are non-transitive, and the same thing is going to occur here. Okay, so let's see what happens. Okay, let's consider who wins between, a war that occurs between die A and die B. So, which die wins? Die A versus die B. Okay. So we roll both die. Okay, die A rolls and die B rolls, and if die A is rolled a higher number than die B, then die A wins. Okay. And so we just use the mechanical approach. So here's what happens. Okay, so you have the start of the experiment. Now you roll die A. Okay, what are the outcomes for die A? Die A can either be 2, 6, or 7. Okay. And then, we roll die B. And what are the outcomes for die B? Die B can be either 1, 5, or 9. 1, 5, or 9. 1, 5, or 9. 1, 5, or 9. Okay. So if I asked you how many outcomes are possible, you would take the product rule. 3 times 3. 3 times 3. 9. Okay. But now we're doing probability. So we need to assign for each of these outcomes, let's assign a name and a probability. So the name, we can just call this name, 1, 2. This is, 2, 2, 1. 2, 5. 2, 9. Okay, 6, 1. 6, 5. And 6, 9. Okay, and then 7, 1. 7, 5. And then 7, 9. Okay. And now let's assign probabilities. Well, we compute the partial outcome probabilities and then the probability. Basically, we add probabilities to the edges. So 1/3, 1/3, 1/3. Why 1/3? Because there are 3 outcomes and each of them is equally likely. Then 1/3, 1/3, 1/3. Again, 3 outcomes each equally likely. 1/3, 1/3, 1/3, 1/3, 1/3, 1/3. Okay. And now 1/3 of the time this outcome occurs. So product rule, 1/9 of the time. 1/3, 1/3, 1/9, 1/9. Okay, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3. But they're all 1/3 times 1/3, so 1/9 for all of them. This is a very special kind of set of probabilities. See, notice they're all the same. Okay, we will see later. We call this a uniform probability space, but that's notation. Okay. We've computed probabilities. Now let's ask our question. Okay. When does die A beat die B? When does die A win? When does die A win? Okay, so that's our question. And so let's answer our question. Well, we need to identify the outcomes where die A wins. And it's not too hard to sort of identify those outcomes. Let me box them. So here, 1. 2, 5, 2, 9, die A loses. 6, 1, 6, 5, die A wins. So 2, 3, okay, and then 6, 9, die A loses. 7, 1, 7, 5, win, win. Win, win. Okay, and 7, 9 loses. Okay, so what's the event of interest? The event that is going to help us to compute this probability, it's just these red outcomes. So the event of interest that corresponds to that question is 2, 1, 6, 1, 6, 5, 7, 1, and 7, 5. Okay? Those are the outcomes. They all have a probability 1/9. So now we're going quickly. The probability of that event, which is the sum of the outcome probabilities, so the probability of this event. But since they're all 1/9, the probability is just the number of outcomes divided by 9. It's just 5 over 9. Boom. So die A beats die B more often than not. So we will say that die A beats die B. Okay, so now I'm going to give you more practice. Do the battle between die B versus die C. Okay, die B versus die C. What's the probability that B wins? Probability that B wins. Okay, and then die C versus die B. What's the probability that C wins? Oh, die C versus die A, sorry. So then that's all 3 battles. A versus B, B versus C, C versus A. Okay. So pause the video. Take as much time as you want to compute these. Good practice. Okay. And I'll give you 1, 2, 3 seconds. And now if you're coming back just for the ride, or if you computed that the probability that B wins the battle versus C is 5/9, and the probability that C wins the battle versus A is 5/9, then you did it right. Well done. You're really understanding the mechanical approach to computing probabilities. Fantastic. Okay, but now we see what's the dilemma. So die B beats die C, and die C beats die A. So no matter what die your friend chose, let's say that your friend chose die B, you pick A. If they chose C, you pick B. If they chose A, you pick C. So having the option to go second in picking is a huge advantage here. You'll win, more than 50% of the battles. And if you're gambling on this, you'll win a lot of money, especially if you play 1,000 battles. Okay? So, this is non-transitive die. Very weird phenomenon. Die A beats B, B beats C, C beats A. This is something that can happen when probabilities are involved. That's why probabilities are so counterintuitive. Okay, so let's erase and now sort of discuss the formal footing of probability theory, which is called a probability space. Okay, and we'll list these sort of experiments that we discuss in the language of the probability space. And speed erase, let's go fast. Bam, 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 bam. Okay, so let's talk a little bit about the formal underpinnings of probability, which have to do with sets. Okay, so let me remind you of the flipping of the two coins experiment. Flip two coins. Okay, and what were the outcomes? Okay, the outcomes were heads, 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 tails, tails, heads, tails, tails. Okay, those were the four possible outcomes. Okay, and the probabilities, okay, were 1/4, 1/4, 1/4, 1/4. Okay, now the set of possible outcomes, we call that the sample space. So the set of possible outcomes we call the sample space omega. Okay, and on this sample space omega, so for every outcome, we have defined a probability. So there's a probability for every outcome. So you can think of that as a probability function P, which takes as input the outcome and produces a probability. Okay? So these probabilities you can think of as being produced by a probability function. Probability function defined on omega. Okay? Interesting. Okay, and so this leads us to the formal specification of the setup for probability. So this pair, which is the sample space, and the probability function, which tells you, which assigns to every outcome a probability. These guys together are called a probability space. Okay, now it's a fancy word. You don't need to panic. Okay, the probability space is just the abstract way that we represent the possible outcomes and their associated probabilities from an experiment. Okay, now, of course, the mathematicians can then divorce themselves from the concept of an experiment and just study probability spaces in the abstract. But for our purposes, we're always going to be attached to some experiment. Okay, so the probability space. Okay, consists of two things. It consists of the sample space, omega. It's the set of possible outcomes. And it consists of the probability function, P of omega, which for every outcome in my sample space omega assigns a probability, just like here, 1/4, 1/4, 1/4, 1/4. And there are certain conditions that we require of this probability function. The first is that it is non-negative and bounded by 1. Okay. And that when you add up all the probabilities for your sample space, they must add up to 1. So the sum for outcomes in your sample space of the probability for that outcome must be 1. And just like here, so you have outcomes, you have probabilities, and they all add up to 1, and the probabilities are non-negative and between 0 and 1. Okay, so this is a valid probability space. Okay, and here's the general definition of a probability space. And event epsilon is a subset of your sample space omega. Okay, and so this is just the formal definition of an event, and it's exactly what we already saw. But I'll just point out that because an event is a subset, you can do the things to events that you could do to sets. So for example, consider the event E1 is that you have matching flips. So this consists of the outcomes HH and TT. Let's consider the event E2 that you have at least one head. At least one heads. So this consists of the outcomes HH, HT, TH. Now you can take the intersection event, you can take the complement event, you can take the union event. Okay, so you can say matching flips or at least one head. So epsilon 1 union epsilon 2, or E1 union E2 is matching flips or at least one head. Okay, and this is the union of these two events, which is just, happens, which is actually all events. So matching flips or at least one head. You can take the intersection, E1 intersection E2. That would be matching flips and at least one head. So matching flips and at least one head is the intersection. This is just the set HH. And you can compute the probabilities of these sets. You can take the complement of an event, and so on and so forth. So because events are just plain sets, they happen to be subsets of your sample space, you can construct other events by doing set operations on events. So that's just to show you some of the power that can arise from formally viewing the probability space within the realm of set theory, or from the point of view of sets. Okay. Now I want to focus on a special property in this probability space. Okay. Now, don't worry, probability space is just the abstract way of referring to this combination of an experiment where you have outcomes and probabilities. But notice that all the probabilities are the same. Okay. And when all the probabilities for all the outcomes are the same, we call it a uniform probability space. Uniform probability space. And so now we're going to study uniform probability spaces. Before we get going, I just want to, give you a couple of pointer exercises. So exercise 15.9 and 15.10, very important exercises for you to do in the text, and the answers are all there for you to sort of see, the notion, get practice with the notion of a probability space, and practice with some of the manipulations that we can do when we're talking about probability spaces. For example, a generalization of the sum rule from counting to a sum rule for probabilities. Okay. So do these two exercises, important. Now we're going to move on to a probability space, the uniform probability space, this is an example. Okay, so in a uniform probability space, the sample space has size, size of omega. So in this case, 4 equals 4. Okay. And the probabilities are all the same, okay? And so the probabilities are all the same. And in this example equal to 1 over 4, which is by coincidence happens to equal the size 1 over the size of omega. Well, that has to be. Why? Because if the sum of the probabilities is 1, so sum of probabilities equals 1, then the only way that the sum of 4 probabilities can be 1 if they're all equal is if each of them is 1/4. Okay? And that's true in a general uniform probability space. So the sum of the probabilities are 1. Okay, this implies that in general, the probability of an outcome in a uniform probability space is exactly 1 over the size of the probability space. Okay, so then what's the probability of an event? The probability of an event is exactly equal to the sum of the probabilities for the outcomes in the event. So the outcomes in the event, the sum of the probability of that outcome, that's the definition of the probability of an event. Okay, and if all the probabilities are equal, so this is the sum of outcomes in my event, the probability of 1 over the size of the sample space. Okay, so I'm adding up the 1 over the size of the sample space for each outcome in the event. So I'm going to end up with the number of outcomes in the event times 1 over the sample space size. Okay, so I'm going to box this for uniform probability spaces. The probability of an event is equal to the size of the event divided by the size of the sample space. Okay, so let's take an example. What's the probability that you get at least 1 heads? So the probability of at least 1 heads. Well, we could identify the events. So here's at least 1 heads, here's at least 1 heads, here's at least 1 heads. So we could add these up. 1/4, 1/4, 1/4 gives me 3/4. Okay? The alternative is to just count the number of outcomes in the event. So at least one heads corresponds to 1, 2, 3 outcomes. So we take the size of the outcome, the size of the event, 3, divided by the size of the sample space, the number of possible outcomes, 4, and we get the same answer. Now, why is this very convenient? This is very convenient because computing probabilities for a uniform probability space exactly equates to counting the sizes of sets, the size of the event and the size of the sample space. Okay, that's what it equates to, counting the sizes of sets. So let's do an example of that. Okay, an example. Okay, and we asked this question at the beginning. You flip 3 coins. Okay, how many heads? Okay, now we are ready to answer this question. We don't know how many heads, but you could get 0, 1, 2, or 3 heads. But let's approach this from the mechanical probability approach. So the experiment is you flip a coin, so you can either get heads or tails. Now you flip a second coin, you can either get heads or tails. Heads or tails. For the second step in the experiment. Now flip a third coin. You can either get heads or tails. Heads or tails. Heads or tails. Heads or tails. Okay, now let's compute probability. So what are the outcomes? There's H, 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 3 heads, H, H, T. Okay, then there's H, 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 T, H, H, T, T. T, H, H, T, H, T, 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 H, T, T, T. Those are the outcomes. How many outcomes? Well, when you flip 3 coins, you can get all possible sequences of length 3, where these are binary sequences, binary because they consist of either heads or tails. And we know that there are 2 to the 3 sequences of length 3. So this is the outcome space omega, and the size of the outcome space is 2 to the 3, which equals 8, and we've verified that here. Okay. Now, let's look at the probabilities. So when you flip a fair coin, now this is where it's important that the coin is fair. Each of these is equally likely and they must add up. So this is a half-half. Half the time heads, half the time tails for the first toss. So half-half. Okay, now once you get to the first toss, when you make the second toss, half the time heads, half the time tails. Half-half, half-half. Okay, and when you get to the third toss, half the time heads, half the time tails. Half-half. And you see all these are going to be 1/2. Okay. So now when we compute the probability, for example, of HHH, we multiply 1/2 of the time, off 1/2 of the time, off 1/2 of the time. So we get 1/8. And you'll see very quickly that it's going to be 1/8 for all of these. So it's a uniform probability space. And no surprise, the probabilities are all 1 over the size of the sample space. Okay. So uniform probability space. Probability space. And so the probability of an outcome, for example, HHH, is equal to 1 over the size of your sample space, which is 1 over 2 cubed, 2 to the 3, which is 1/8. Okay. Now we can ask, what are your chances of getting 2 heads? Okay, chances of 2 heads. Well, in a uniform probability space, it's just the number of outcomes in the event, 2 heads. Okay, so the number of sequences of length 3 with 2 heads, the number of binary sequences with 2 heads, that's the same as the number of binary sequences with 2 ones. Okay, so probability of 2 heads equals number of outcomes with 2 heads divided by the size of my sample space. Okay, which is equal to the number of outcomes with 2 heads. Well, that's 3 choose 2 divided by 8. Okay. And you can go and compute that, it's 3/8. But we can now compute the probabilities for all the possible number of heads. So you can have number of heads. Okay, you can either have 0, 1, 2, or 3. Probability. Okay, 3 choose 0. So this would be 3 choose 0. Choose 0 divided by 8. 3 choose 1 divided by 8. 3 choose 2 divided by 8. And 3 choose 3 divided by 8. Okay. Why? Because the size of the event is the number of sequences with 0 heads. The number of sequences with 1 head, that's 3 choose 1. The number of sequences with 2 heads, that's 3 choose 2. And the number of sequences with 3 heads, that's 3 choose 3. This is 1/8, 3/8, 3/8, 1/8. So, We can't answer this question, how many heads you get. But we can tell you what are the possibilities. You can either get 0, 1, 2, or 3 heads. And we can tell you how likely each is. 1/8, 3/8, 3/8, 1/8. So the chances you get 2 heads is 3/8. The chances you get 1 head is 3/8. What that means is that, if you repeat this experiment many, many, many times, 3/8 of those repetitions will have 1 head. 3/8 of them will have 2 heads, and so on. Okay. So that's an example of, a uniform probability space. Okay, so exercise. You flip 4 coins. What are the chances of getting 2 heads? Okay, so now that's an exercise. And I'm going to, just tell you that the outcomes are, the sequences of length 4, binary sequences of length 4, binary containing heads or tails, and it's a uniform probability space. Okay, now you can sit down and think about that. Okay, but now pause. I'm going to give you a few seconds. 1, 2, 3, 4, 5. Pause the video. Okay, and work it out. Okay, 1, 2, 3, 4, 5. Now, okay, if you pause the video and work it out, or you just want to see the answer, well, we're interested in, the sample space size, is all sequences of length 4. This is 2 to the 4. Okay, and the outcomes with 2 heads, how many are there? There are just 4 choose 2. So 4 choose 2, okay, which is equal to 6 over 2 to the 4, which is equal to 6 over 16, which is equal to 3 over 8. So the chances of 2 heads is 3/8. If you got that, fantastic. If you didn't, okay, sit down and work through it. Okay, and in the text we show an example of using a uniform probability space to compute things like the probabilities of various poker hands, like flushes and full houses and so on. So if you're into poker, have a look at that example. Okay, let's erase, and we'll be back. Okay, so, this chapter has been about, computing a probability, basically how to analyze an experiment, okay, whose outcome is random. Okay. And so what we do is we first analyze the possible outcomes, and then we attach probabilities to those outcomes, and then compute, ask a question which defines a subset of the outcomes, and then compute the probability of that subset. Okay, and so read chapter 15 carefully. Okay, and do all the exercises and become good at computing probabilities. Now I want to show you something, a little bit more complicated, and that's how we'll end this lecture. Okay, which is we'll answer the second question that was posed at the beginning, which is you toss or you flip a coin, okay, randomly until heads. Okay, how many flips do you make? How many flips do you make? Okay, so let's analyze this. Okay, so let's see how this experiment goes. In the first flip, one of 2 things happens. You get a head or you get a tail. Okay. Okay, just like the regular situation of flipping coins. Okay, now if you get a heads, the experiment's over because you flip the coin until you got a head. Okay, so the experiment's over. But if you get a tail, the experiment is not over yet. Okay, so you have to keep flipping until you get a head. So you'll flip again. You could either get a heads, or the problem is you could get a tail. Okay. In this case, okay, here the outcome is H. Here the outcome is TH. Here the outcome is not yet determined. The experiment is not yet over. So you keep flipping. You can get a heads, or you can get a tails. Okay, so here the outcome is TTH. You stop. And problem is it's not yet over. So you flip again. H or tails. And here the outcome is TTTH. Okay. When will this experiment end? This is a bizarre experiment. This is a bizarre experiment. It can go on forever. This experiment can go on forever. Okay, but that's not a problem. Okay, there's nothing that says an experiment has to terminate. Well, eventually, when it stops, it'll terminate with a finite number of flips. But when we're considering what are the possible outcomes, they can go on forever. In principle, you could toss any number of tails before getting the first head. Okay. Now, the outcomes are, H, TH, TTH, TTTH. Then the next one here would be T, 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 TH. So we can write this as T cubed H just to be simpler. Okay, and then the next one would be t to the fourth h, and then t to the fifth h, and so on. Okay, so if I'm writing my outcome space, okay, to look at my probability space, my outcome space consists of h, th, t squared h, t cubed h, t to the fourth h, t to the fifth h, and so on. So my sample space, my set of all possible outcomes is infinite. Okay, that's why I said this is a slightly more complicated, example. And now, what are the probabilities? Probabilities. Okay, so associated with this sample space, to get a probability space, I need to assign probabilities. Okay, and so let's see. So let's just do it the usual way. So you have a half here, a half here, a half here, a half here. That's because each toss is a fair coin. Okay, so a half here, and so on. So the probability of this guy is a half. This guy, half times half. So 1/2 squared. This guy, half times half times half. 1/2 cubed, and so on. So this is a half squared, a half cubed, a half to the fourth, a half to the fifth, and so on. Okay, it's not a uniform probability space. Okay, but is it a probability space? So are all the probabilities non-negative? Yes. Do they sum to 1? Let's see. So 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the fourth plus that is equal to 1/2 over 1 minus 1/2. So this is the famous infinite geometric sum, and if you don't know about it, read up about it in the summation chapter, where we gave you the common sum for an infinite for a geometric progression. So, or take this from me. Hopefully, you've seen it before, the infinite geometric sum, and this is equal to 1, as expected. Okay. Now, interesting question. So let's analyze now an interesting game. Okay. So you and a friend decide to toss coins. Okay. You flip a coin. Okay, and the first person to get ahead wins. So, take turns, flipping. First head wins. Do you want to go first or second? Okay. So, let's see. Let's imagine that you go first. So this is an example of, you're taking turns to succeed, and do you want to be the first to get a chance to succeed or the second to get a chance to succeed? So let's say you're the first to get a chance to succeed. When do you succeed? You succeed here. Okay, you succeed. So you win. You lose. Because, you tossed a tail and then your friend tossed a head. Here you win because you tossed a tail, friend tossed a tail, you tossed a head. So you win. Here you lose. Okay, because you tail, you tail, friend heads. So friend wins. Okay, here you win. And so on. You see that the outcomes that correspond to you winning are exactly the odd powers of 2. So the first head wins. So the event that corresponds to you winning is the event, h, t squared h, t to the fourth h, and so on. Okay. And the probabilities of these are 1/2 cubed, 1/2 to the fifth, and so on. So the probability of this event is equal to 1/2 plus 1/2 cubed plus 1/2 to the fifth plus and so on, which is equal to 1/2 over 1 minus 1/4, which is equal to, so the common ratio between these terms is 1/4. So the sum of the infinite geometric progression is the first term divided by 1 minus the common ratio, okay, which is 1/2 times 4 over 3, which is 2/3. Interesting. So we've come up with an interesting sort of tidbit. Okay. If you're engaged in this game of you try something, okay, and if you win, game over. If you fail, I try, and if I win, game over. You try, I try, you try, like that. If you're interested in this if you're engaged in this kind of a battle, okay, then going first gives you a 2/3 chance of winning. Question, what about going second? So your friend, what are your friend's chances of winning? So probability that first wins equals 2 over 3. What about the probability that the second wins? Okay, now we could compute this complicated summation again, or we could realize that either you win or the second wins. Either first wins or second wins. So so the probabilities of those have to add up to 100% or 1. So this must be 1/3. So your chances of winning in such a battle are twice as likely if you go first. So be the aggressor, go first. Okay. And this kind of analysis applies to all kinds of situations. For example, a startup. If you're the first to market, you are much more likely to be the winner than if you're second to market. Because if you're first to market, you are the one who will get the first customers. Okay, with high probability, with let's say probability a half. You might not get the customers, okay, and then the second to market might get the customers. But then if they don't get the customers, now it's your chance again to get the customer, and so on and so forth. Okay, so this kind of a tit for tat battle that keeps going on occurs often in practice. Okay, and here's an analysis that shows if you're first in this attempt to win, you are twice as likely to win. Okay, so that's probability. Some of the uses of probability. Okay, read chapter 15 carefully. Get good at computing probabilities. Checking out.